Right, so oh, nice. Good. Let me start sharing my screen and I'll take it from there. Actually, let me... Yeah, okay, this should work. Right, so yes, hi everyone. As Harsha has just said, my name is Ivan. I am indeed lecturer of marketing analytics, and I'm also a marketing director of the Center for Marketing Analytics and Forecasting. This is the center that was founded by Robert Files back in 1995, I think, or something like that. And this is a center that does lots of different projects in the field of forecasting and related areas. I must apologize, I have cold or something like that, so I might make these weird coughing noises from time to time, but hopefully that won't ruin the whole workshop. Right, so what else? As Harsha said, I'm a creator and maintainer of several packages, and here are 5 of them. Something new that some of you have not probably seen is the package called Complex, and you might hear about it later in May, I think, because we're working on that with colleagues. Right, so these are the packages, and the main thing that we will discuss is the stuff implemented in the Smooth package for R, and that thing is called Atom. Right, but before we move to Atom, let's see how we will work today, right? So the plan is the following. We will start with a very brief introduction to ETS, exponential smoothing, in state space form. Then we will discuss how to incorporate explanatory variables in it, how to deal with intermittent demand, and then we will finish with the multiple seasonalities. These are all things based on the Atom monograph, and the format today will be very short lectures where I will tell you some things, hopefully not going into, well, we cannot go into much depth anyway, so it would be quite light without much mathematics and so on. And then we will have examples in R and Q&A. You will be able to ask questions, and then we'll move to the next topic. So that's the rough idea. And as I said, this is based on the following. This is the monograph that I've written. It's available online. The text is available online, and if you scan this QR code, it will lead you to this website. There's also a physical copy which you can buy if you want, but actually the online one is updated. Still, even now it is updated slightly. I'm finding some errors, or I'm expanding some parts and bits and pieces. So maybe in a couple of years there will be second edition if anyone wants that. Right. So that's the thing, and we can start moving to the introduction, I think. I typically like some silly things on my slides just, to distract people. And one of these things, through these slides, I decided for whatever reason to use Star Wars. And this is the introduction to Star Wars, and in our case, it's introduction to the ETS, right? Apologies for that again. ETS, what is it? ETS stands for Error, Trend, and Seasonal. This is a model that underlies a taxonomy of a family of models. It is so-called single source of error. There is also something called multiple source of error, but it is a separate model which is estimated differently and probably much more flexible than the SSOE one. State space here means that the model consists of 2 parts. We have measurement equation. It shows how the data is decomposed into different components, right? So we see some sales, and measurement mathematically shows what the sales consist of. And then there is transition equation, which shows how these components that we've sort of identified or assumed, how they change over time, how they evolve. So having these 2 fundamental things gives us this nice big model, which is flexible and easy to work with. This single source of error means that we use forecast error in the measurement equation and in the transition equation. So the states updated based on the forecast error. And that's the important element here. Okay, so what is it? Here's an example. This is ETS AAA. What does it mean? It means that it has additive error, additive trend, and additive seasonality. And it is formulated mathematically like that. I said that I wouldn't have too many formulas, and I think this is one of the few ones that we have, but I think it is important to at least see to understand what we have here. So the first part here is called measurement equation, as I said. And it tells us that we have level component, we have trend component, for whatever reason it's denoted as B, and we have seasonality S. And then there is an error term, you know, white noise or something that we cannot predict. And as I say, this is measurement. It shows how we decompose the sales, and then we see how level is updated over time, how trend is updated, how seasonality is updated. Alpha, beta, gamma here are the smoothing parameters, and they regulate how fast the model reacts to the noise, to changes in the data. So for example, if alpha equal to 0, then this bit will disappear, right? And we will be saying that level is just previous level plus trend. So it will be just growing, increasing trajectory. And if it is equal to 1, then typically the model starts exhibiting sort of random walk behavior. Right. What else? Here is a nice graph showing how the things are decomposed. So this is the black line on this plot is the actual value, the purple is the fitted value, the blue is the forecast, and this red line is the origin from which we produce the forecast. And we see how level changes over time. You see that it increases all the time, and that seems to be correct because indeed we see the increase in the data. The trend for this specific situation does not change at all because I think when I estimated this model, the beta was equal to 0. And if you think about it, indeed it might not be needed anyway, because the trajectory is quite straightforward. Then there is seasonality, and spoiler alert, this data has multiplicative seasonality. What does it mean? When we look in the beginning of time series, the variability is low here, but when we look at the end, where the level is higher, the variability is higher. This is characteristic of multiplicative seasonal model. But because we use the additive one, we see that there is a increasing seasonality here, which sort of tells us that we did something incorrect. But the point of this plot is just to show you how things are decomposed and how they evolve, right? So the last bit here, slightly misaligned for whatever reason, I think, or is it? Maybe not. Anyway, the last thing is the error term. Cool. As I say, I'm not going into details of these models. The monograph has all the details if you want. But how do we estimate the model? The conventional ETS assumes that the error follows normal distribution. Why do we like normal distribution? Because it's convenient. Although I should have cited a friend of mine when I asked him about the pronunciation of some English word. He's an English guy. He told me, because shut up. So I should probably have said something like this. Why normal distribution? Because, you know, yeah, that's what we like. And when we fit the model, the straightforward thing to estimate is to maximize likelihood. If you're not familiar with these things, go to the monograph. Now, parameters have some bounds, and they all guarantee that model forgets older data in one way or another. So this alpha, beta, and gamma, these are the smoothing parameters I'm talking about. There is usual ones, which guarantee that the model somehow averages the data. There are traditional ones. So if you have heard about exponential smoothing, you probably have heard that smoothing parameters lie between 0 and 1. This is the traditional bounds or conventional classical bounds. And this is not entirely true. In some situations, this would be too wide. Right, but that's not an important bit. And then there is the third one, which is admissible. And they make sure that the model is stable, so it forgets the past, roughly. or at least so-called forecastable. Forecastable means that the impact of the first observation on the final forecast does not increase over time. These are simplifications, both of them. So there is mathematical definition of both of these terms, but I thought that expressing them in this simple way should help. And why do we need this? Because we will come back to that in the next chapter of this presentation. Okay. In ETS, components can be added or multiplied. This sort of gives us this zoo of models. Error can be either additive or multiplicative. So in the previous plot, when we had the equation, it was additive, right? So we added it, but we can multiply the structure by the error. Trend can be, and there are 5 options here. You might have no trend, and this is entirely fine. You might have additive or additive damped trend. Sorry, typo here. Additive damped trend is the one that slows down somehow over time, because you don't expect your sales, for example, to increase indefinitely. They will be slowed down somehow, you know, because of competitors' behavior and so on. Then there is multiplicative, which exhibits sort of explosive behavior, explosive increase or explosive decrease. Maybe implosive decrease actually. And then multiplicative damped, which has similar characteristics to additive one. And we have then 3 seasonality: no seasonality, additive, or multiplicative. And as you can see, we can have all the combinations of models with different components, which gives us overall 30 models in this framework. This becomes not a simple task. You need to choose the best model from the 30. How do we do that? Well, using information criteria. We'll come back to that. And here you can see some examples of models. So in the columns, I have different types of seasonality. The first one is no seasonality. And this is the very basic, simple, you know, level time series. Seasonality can be additive, as I said, or multiplicative, and you can see the difference. Here, for example, now let's take this one. ETS AAA that we looked at. So this is the data where it would work perfectly. You can see that the seasonality in the beginning, the amplitude is roughly the same as in the end, right? So it's not expanding, so this is additive seasonality. And here is the AAM. We can see that in the beginning the variability is small, but at the end it expands. So yes, it is multiplicative. And then different types of trend, and here is, for example, multiplicative trend, which exhibits, as I said, explosive behavior, and this is damped, as you can see, slows down. But these are all additive error models, and here are the multiplicative error ones. And you can see that they are very similar fundamentally, this plot with the previous plot, right? But notice, for example, ETS AAN, you can see that there is a bit of variability with additive error, but in the beginning and in the end it's quite similar. When we talk about multiplicative error, the variability starts increasing a little bit. So that's a similar idea, you know, because you multiply things, then when the level or baseline increases, then the variability increases as well. Anyway, you can see the whole zoo of different models based on these 3 components, based on this structure. Right, so how can we select the best one? The conventional approach is the following. You create the pool of models. By default, you can actually have all of them, all 30 of them, but that might not be meaningful in your specific situation. Then you feed all the models, and you select the one that has the lowest information criterion. For example, AIC, so Akaike information criterion, or the default one in many functions in R is AACC, or whatever else you want. But the process is like that. You can actually also substitute this step with AIC with something else. For example, hold out RMSE or whatever other error measure you want. And then that would work as well. But this approach is just relatively fast and simple, and it works quite well. So when it comes to R, there are several packages and functions that implement ETS, there is the good old ETS from Forecast package. Good old because it was introduced in 2006 or 2008, I think. Probably 2008, by Rob Heinemann, and it's very popular. There is a newer version of ETS from the Fable package. And then there is ES from my Smooth package, and there is Adam that implements ETS as well from Smooth package. The difference here is that Adam implements many more features, while ES, it's just the basic exponential smoothing in a similar form like this, but with additional bells and whistles in comparison with the Forecast. So what's the issue here? You see, everything's fine, right? Because we have such a great approach with so many models and easy to select, to estimate, and so on, and we have functions. Well, the conventional ETS works well on high volume, low frequency data. So for example, monthly data, quarterly, and so on. It assumes that, as I said already, that the error term follows the normal distribution. And this is fine when you deal with this type of data. But when your volume decreases, then you might see some issues. Or when you work not with sales, but with something else, for example, with some financial data, you wouldn't expect things to be normal anymore. So we need somehow to simplify this, right? And it's not very clear what to do with that, right? It's not designed to capture intermittent demand. Well, we actually think that intermittent demand is a separate thing, which is why we should use other approaches. But well, who told us that? Maybe we can modify it and use it. And we will discuss that later in this section. It does not support multiple frequencies is another thing, and there are some modifications for that, and we will discuss that as well. But one of the pressing things is no explanatory variables. Neither ETS from Forecast nor from Fable support explanatory variables. And this is an issue, and we'll come back to that. We'll discuss that in the next chapter. So Adam that I mentioned is an extension of ETS. It supports all of those features and maybe and many more. And in today's session, we will discuss first ETS-X, so it's ETS with explanatory variables. Then we will move to IETS, intermittent demand modification, and then we will discuss the multiple frequency one. But first, let's do a small exercise. And to do that, I would kindly ask you to follow this link. Let me see, can I actually somehow remove this pane? I don't know. Maybe you don't see this thing, but I have this from Zoom. I don't know how to remove it. Fine. So I will kindly ask you to follow this, scan this QR code, follow this link. This will lead you to my website where I have the event, this event, and there is the first link in the event which says R file. Let me check myself. It should be there. It says files for the workshop. So if you download that and extract and open, oops, sorry, misbehaving a little bit. Then we will see what we have there. So we have there a small exercise. I will guide you through it. Should actually share the second part of my screen. How do I do that? Okay, maybe I'll just move things. Has everyone, let's assume that everyone opened that. Maybe Harsh, you can paste the link to the chat. Thank you. So this is my lovely R. Do you see my R screen? Yes, you do. Because I'm not sure already how I shared the screen. Things might disappear. Right. So this is the R Markdown file with the workshop. You have a different one because you have the PDF version. Let me just demonstrate how it looks. Something like that. Content, and you have code and some suggestions, but I will move to R Markdown because it's easier to run things here. Right. What are we doing here in this workshop? In this workshop, we will just have a look how the basic function ES works from the smooth package. As I said, it implements more things than ETS. This is why we will use it here, although the syntax for ETS would be quite similar. And the first thing is we have this beautiful time series from M3 competition. To run it, we will need to install the mcomp package. And to do all those things, you would need to install smooth package. I will actually guide you, and maybe you can have several minutes afterwards to do that if you want. So let's see. The first thing, you see the code is very simple here. You're just calling the function and you give the data to it. And when we run it, it tries all the models. It uses a slightly smarter approach than just fitting everything. It goes through specific models and decides whether to use seasonality, to have seasonality or not to have seasonality. Okay, but it does that, and when we run summary, we will have an issue here, I think. Yeah. Anyway, let me open. Oh, this panel is not helping again. So the summary of this thing looks like this. And what do we see here in the summary? It shows us what model was estimated, or what was selected actually. It's ETS MMDM. Do you see my screen? Should I zoom in maybe?
Yeah, a bit maybe.
Is it okay? Perfect, good. Right, this is the model that was selected for some data. The distribution was normal because, as I said, the default ETS assumes normality. We used likelihood, and here is the loss value for whatever reason. And then we have a set of parameters. Alpha, beta, gamma are the smoothing parameters of the model. Phi is the dampening parameter. Then we have initial level, initial trend, and 11 seasonal indices. And we see the estimates of parameters. Alpha is quite small, beta is quite small, and there is also a bit of uncertainty around it. Standard deviation, not very informative, but here it is. And there is a warning which happens when you run this summary, because typically the likelihood does not reach the maximum. It's pretty close to maximum, but maybe it's not. And sometimes it's difficult to invert matrices, so it might complain, but I haven't been able to resolve that issue yet, and maybe that's not a big deal. Okay, so you see this is some sort of summary, some information about how model did things. But the good thing about the smooth function is that we can have this beautiful plot method, and by default it will produce this 2x2 matrix of images. And the first one is just fitted values from the model versus actual values, and you can see that overall we probably would say that the model captured tendencies well. These are actually standard plots when you want to do the analysis of residuals and want to understand how to improve the model. For example, absolute residuals versus fitted is typically used to detect heteroscedasticity. We do not seem to have anything serious here. Standardized residuals, we can use it to see whether we have outliers. There are some levels lying further away, but maybe they are not important. We could investigate and see what happened in those observations, but I wouldn't spend time on that today. And then there is QQ-plot showing how our residuals look versus the theoretical ones. And in this instance, we assumed normality and everything seems to be pretty close to normality. There is a little bit of, further away in the right tail, which could be due to outliers that we see here. Once again, we could investigate and see whether this is serious or not. The deviation from normality, by the way, in our case, would mean that our prediction intervals might be wrong. So that's why it is relatively important to see whether our assumptions are correct or not. Anyway, so we've fitted the model, we can do diagnostics, we can then improve it further if we think that there is room for improvement, and we can produce forecasts from it. So when we do, here is what we get. This is from ETS MMDM, and the purple line is the fitted value, the black is the actual, and as I said, the blue is the forecast. And here is actually the thing that we didn't capture well. Probably this is indeed an outlier. The tendency, was the seasonality. The peak here was much lower in all the other seasons, and in this one it was much higher. We could somehow go to the data and trying to understand what happened in this month, but this is slightly outside of the scope of this introductory exercise. So this is an example of how things are selected by default, and the default pool of model is defined by this command. Model is ZXZ. Documentation explains what these things mean, but roughly it will try all types of error, all types of seasonality, and only non and additive trend. Why this way? Because actually multiplicative trend might exhibit explosive behavior, and in some cases, if you do that automatically, you might be asking for trouble. At least from my experiments that I did on different data sets, when you do this, you allow the model to select multiplicative ones. Sometimes it overfits the data and then everything explodes. Okay, but we can actually amend this pool, and we can form our pool or form a predefined one, or use the predefined one. And for example, we could use YYY, and YYY would tell us that we are testing only the multiplicative components, or XXX with pure additive ones. Or we can actually create a custom pool. So I encourage you to experiment with different options of the function and see what happens. Given that this was automatically selected as ETS MMDM, I bet that if I run this, I would probably get the same model. Yep, MMDM. That's the best for this data, seems to be the best for the data. All right, and we can have other combinations. For example, MZM. If we do this now, we will get exactly the same model. So nothing fancy here and nothing exciting, I would say. But this data is actually quite well-behaved data, and I love this. I love this time series because it has such a clear seasonality in it. It's very good toy time series. Right. Actually, my friend Nikos Kourentis makes fun of me when I say that I love this time series, because he says that I need to do something with my personal life then, because loving a time series is not a good thing to do. Right. So this was all about selection, and I'll give you, as I said, a bit of time to experiment. But there is another bit which sort of shows you why ES is useful. These pools that we define here, especially these ones, are supported only by ES. If you use ETS from R, you wouldn't have it. But another important thing is the combination of models. The idea was explored by Stefan Kalasa in his paper 2011. You have the reference in that workshop file, and what's the idea is that we feed a pool of models, we extract information criteria from it, and then we calculate so-called AIC weights. And after that, we produce forecasts and weight everything using those weights. So that's the mechanism that is supported in the ES. If I run it, it will take a bit of time, maybe 5 seconds or so, even faster, 2.5 seconds. And what it did, it just fitted 30 models and combined them. Well, actually not the models, but forecasts from them. So when let's see what sort of weights we have. So here's the depiction of weights. we see that there are two strong models in the pool. The first one, MAM, so additive trend, and it has a weight of 0.35 or something like that. And then the second one, which we selected, which was MDM. There is the third one, which is MMM, but it has a quite small weight, and all the others, you know, weights pretty close to zero. So this is an interesting plot on its own, because it told us, you know, you've selected this model, but how can you be sure that this model is correct? So why didn't you choose this one? Was it just because you had this shape of data in your specific sample? What if you had a new observation? Would the picture change? And most probably it would, but probably slightly. But the point here is, you know, instead of putting all the eggs in one basket and betting that this is the best model, we can try to combine forecasts from these. We will give more weight here, slightly less here, even less here, and then almost nothing to all the others. Okay, and we can combine and we can produce forecasts. Let's see what happens. Here is MS. But you can see what the function did, right? Roughly. So it fitted all those models, it produced forecasts from each one of them, and then combined those forecasts. The gray lines here are the prediction intervals. Actually, if I switch them off for a moment, the forecast will be much clearer, and you can see that it's not very different from the one that we've had before. Where was it? This one. They are pretty similar. Why? Because this model has a very high weight, right? And the prediction interval is combined as well. There are different ways how to combine prediction intervals. There's a huge amount of literature on that, but the method implemented here is quite simple. You just take quantiles, use weights, and you combine quantiles. It was shown that when you do this, then your prediction interval most probably will be miscalibrated, but it is a simple thing to do. So you don't need to do any additional tricks. It's fast and simple and gives you an answer in less than 1 second. Okay, but here we had a pool of all the 30 models. We can actually have our own if we want to. So for example, if I just want to consider these models, I would tell the function, oh, I use Adam here, but should have used ES, but they both work equally, have similar syntax. So we will tell it to use these 4 models, and we will add something like C and N, and C sort of triggers this mechanism of combination. If we run it, takes time, it says that combine 4 models. Okay, and actually let's see, I'm curious if we produce forecast for 18 steps ahead and then plot it, what will happen? This will happen. And because the data is well behaved and this model has the highest weight, the result is very similar to the one that we had before. Right, so you can experiment with different combinations of MCM, YZC, or whatever else. Whenever you experiment, just keep in mind what sort of data you have. You know, if you have high-level positive, high-volume positive data, fine, you can try all these combinations. Probably things won't break. But if you have low volume, then you might need to use to restrict the pools to something more straightforward, like pure multiplicative models. Try to avoid the mixed ones. Harsha, should we give 5 minutes for people to to things? Okay. So let's. I'll give you 5 minutes to explore, and we'll continue in 20 to 11. Should have invented some beautiful timer for that. And if you have questions in the meantime, maybe we can actually have Q&A. Let me see. Sorry for that. There are some things in chat. Yes, the link. Oh, was the bit.ly wrong? Sorry for that. Page not found. That's a shame. I see a question in the chat from Marco, a very good question. So the question is, how are the weights of the ensemble model calculated? Yeah, you didn't miss it. I didn't explain it in detail. The rough idea, we extract information criteria from each of the models that we fit, and then we use the formula. There's, I don't know. I don't think it is worth showing. Then we use a formula which sort of calculates weights based on these AACs, based on all the AACs. So this way, the model that has the lowest information criteria will have the highest weight, and the one that has the highest information criteria will have, well, the other way around. So we sort of guarantee that bad models do not contribute much, and the best ones have a good contribution. This is based on Stefan Scalassa paper, indeed, yeah. And this is also explained in the monograph in, I don't remember what chapter. Thank you. Right, let's see. Should we continue, or do people want a little bit more time, or are there any questions related to introduction to ETS? While you're thinking, I'll pour some tea.
I guess we can continue.
Okay.
Oh.
Okay, thank you. Right. Okay, let's move to our presentation. Where was it? Where was I? Okay, now we can move to the ETSX explanatory variables. I have this silly image of the combination of the meme and then Star Wars. Messy timeline. Okay, I'm not going to go into details of what I think about all those things, especially after 1, 2, 3, and 4, 5, 6. Never mind. So why ETSX? ETS actually works well, as I said, on data when we don't have any external effects, right? So we don't have any promotions, no prices, nothing impacts our sales. Beautiful. Doesn't happen in real life very often. So in reality, we have lots of different effects. Even we have, things that look like outliers. And if we talk about sales forecasting for a retailer, then promotions is one of the things that drives them, and price changes would drive them as well. And there is lots of things. And yes, if we can capture them, then we would improve the model. But ETS, the default one, cannot do that. So ETSX was first mentioned in chapter 9 of Heinemann et al. Monograph. The monograph is actually focused on single source of error state space model underlying exponential smoothing. So everything that we've discussed so far is from their book. It was then used and extended by Euler et al. In their paper when they tried to somehow deal with outliers. And they proposed several mechanisms and showed that, it works fine. Then there is paper of Korenzis and Petropoulos. It is focused on their own thing called MAPA, multiple aggregation prediction algorithm. But they also investigated ETSX there, and they showed that, ETSX works better than ETS, which is apparent, right? You have promotions, you should take them into account. Ramos et al. Used that as well, and it worked well for them as well. That doesn't mean that it works universally. For example, Mahdi Abolkasemi with his co-authors used it and it worked poorly. I suspect that I know that they used Smooth package, one of the older versions, and I suspect that there was a bug there, which I fixed since then. But, okay, it is what it is. It's published, and the version 2.5.0 didn't do very well. But when we look at more recent things like M5 competition, then ETSX did better than ETS. So we have lots of evidence in the literature saying that, if you have explanatory variables, if you want to use ETS, use ETSX. Okay, how is it formulated? We'll have a couple of formulas here. Stick with me. The main idea, we should align how we include them with the error. So measurement equation, for example, for the additive error model of ETSX would look like this. And this looks like a simple regression. Well, not a simple multiple regression, right? Well, simple multiple regression, something like that. We have first explanatory variable, second, blah, 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 and we have parameters for them. And then we have A0, and you can see all of them have time indices now. A0 t-1 is the ETS part. So it would include level, trend, seasonality, depending on how you define your model. And these things, well, in the simplest case, we are just saying that, A1t is equal to A1t-1. So they don't change, it's just fixed parameters. In this case, we are saying that, this is a static model because all these parameters for explanatory variables do not evolve over time. And this is fine, this scheme works quite well in many contexts, and all these papers that I mentioned before, they use this idea, this approach. If we use multiplicative error, as I said, we need to align with the error. We can actually formulate the measurement equation in logarithms and say that log sales is This is our ETS structure plus, once again, parameter times variable and so on and so forth, and then the error term. And if we take exponent of both sides, then we will see that this becomes a multiplicative model, right? Because we will have a0 t minus 1 times exponent of this times exponent of that, and so on. And the main fundamental idea of ETSX is that we add explanatory variables on top of the ETS. So we have already assumed some sort of structure, and then we want to improve on that. And this thing, the first element, behaves like a time-varying intercept in the model. And this can capture, as I said, trend and seasonality. Now, the note from me is, from my personal experience, trend is rarely needed in ETSX because typically you have some drivers that have trend in them. But in some exotic situations you might need it, so yeah, do explore. There is another thing, the dynamic model, and it is possible to introduce time varying parameters in ETSX, so allow those A1T to evolve over time. They would not be independent, so this is not the same model as the classical TVP that some of you might have used and worked with when you use Kalman filter to estimate things and so on. So this will be quite limited, but it's useful for categorical variables. And the idea of the implementation is the following: if we see x here, then we use this formula, and roughly it becomes our smoothing parameter times error divided by the value of the parameter. And this is the updating mechanism, and it looks very, very similar to the one that we've seen with the ETS, classical ETS model. And if x is equal to 0, then we do not update that. Then we are saying that the parameter is the same. With the multiplicative error, the idea is similar, but we use logarithm of the error instead of the error here. So these are the details, right? As I say, have a look at the monograph, it explains that in more detail. But the main message here is you can see that the same error term is used in the update of the parameters. So when we look at the data, I applied this ETSX A and N to seatbelts dataset from R. We have level of our time series with which evolves over time somehow, and we have the parameter for the kilometers, which evolves somehow over time as well, and we can see that they have very similar shapes. In fact, we can even see that when drop happens here, for example, we have negative error. Then all of a sudden the level goes down and the value of parameter goes down as well. So you can think of it as a bug, or you can think of it as a feature. So because that's what the structure of the model assumes. It just assumes that the parameter uses the same error, and as the result will have the same dynamic as all the other components of the model. If you think about it, all the components of the model will have this feature. So trend will behave similarly, just repeating the data. Okay, the dynamic ETSX, from my personal perspective, is suitable for categorical variables, as I said. So I give some examples, some artificial examples in the monograph. You can have dynamic promotions, for example, over time, and you might suspect that effect might change. So in that case, this works quite well. And there is nice connection between this model, ETSX, and the seasonal ETS. If you use dummy variables for seasonality and update them, then you will end up with just conventional ETS. One thing you can do, if you use some explanatory variable which is not stationary, you can take differences and use the differences in the data. In this case, the model will revert to something discussed in the Osman and King paper 2015. They focused on the model which has explanatory variable in differences. Okay, what else? Parameter bounds. Now, The reason why I have this slide is because if you start Googling about the ETSX, you might find a blog post by Rob Heinemann, who refers to Osman and King paper, this one, and says that, you know what, ETSX is not stable, which is why it should not be used. But this stability thing, it comes from something, from the property that we discussed earlier, from the bounds of parameters. Basic ones for the ETS components apply widely here, so you can use 0, 1 and so on. But if you check the stability and forecastability, which as I say have the mathematical meaning behind them, then they will be always violated in ETSX. And this is not because the model is bad, this is because of how model is formulated. In fact, if we actually get rid of ETS part, let me come back to that formula. This one. So if we get rid of this part, or say that it is fixed, we will end up with pure regression, right? It will be just a regression with all the explanatory variables and no dynamic at all. So if we do that, then, and we check the stability forecastability, then they will be violated as well. That doesn't mean that regression is not useful, that you should not use it for time series and so on. It just means that we are doing something wrong when we check these conditions. So we need to check them differently, long story short. The way to do that with ETSX is to just check stability and forecastability for the ETS part, for the conventional thing, the model, and ignoring the X, because X sort of causes all the problems here. And we know that adding X works in general. Right, so this resolves this dilemma, and I guess it's time for another exercise. Let's see what I have here. It should be TSX, so this workshop. And it looks like this. What do we have here? It's just a simple exercise with some data set. We are using now the Greybox library, which is installed by default if you've installed Smooth. And we will see the case of promotional data. Let me walk you through in a similar way as I've done with the previous part with this workshop. So we have promotional data. If we plot things, it looks like this. Isn't it beautiful? So this is weekly data. That's why we see long cycles here. As a side note, ETS, conventional ETS from forecast package and from Fable does not work, does not allow fitting seasonal model on weekly data. ES and Adam do that. That's because we might end up with huge amount of seasonal indices, and you need to be careful at estimating such a model. Anyway, what do we see here? We see two types of promotions. I don't remember what they were. It's promo 1, promo 2. They are called promo 1, promo 2. And there are some cases when they happen at the same time, and we might have some interaction effects here. And we can see actually that some of these promotions indeed drive sales, right? They increase the values, increase the sales. Right, I even have some questions in this workshop. What components do you see in the time series, and are the promotions influential? So I would say that well, obviously we always have level, and we see clear seasonality, seasonal pattern. So two components. Trend maybe not, it's not clear. I would go with just level model. And promotions, yeah, some of them are influential. We cannot tell for sure that they always work. In order to see the relation, we can use this neat spread function from the gray box, which produces the following plots. So we have Y, which is sales. We have promotion 1, promotion 2, and price. And this is the classical scatter plot, and we can see that there is indeed a relation between price and sales. We can see that it's non-linear, and actually there is heteroscedasticity, right, in the relation, because price here has much bigger variability than at the end of the date when the sales go down. And in terms of effect of promotion, promo 1 seems to have a clear effect. These gray dots here correspond to the mean values. So yep, we can see that there is an increase in mean and the box plot is higher when promotion happens. With the second one, it's not obvious. And these plots just sort of a heat map. It shows you how promotions happen. You see in the majority of cases, we neither have promotion 1 nor promotion 2. Okay, so this is not very informative in this specific setting. Okay. What do we think about relations? We've just discussed. Now, we can try fitting a model. One of the simplest thing is to include both promotions. And now we use the Adam function. We give it the whole data set. For now, let's start with the ANN model. So additive error, no trend, no seasonality. And we are saying that our sales include promo 1, promo 2, and that's it. Let's see. Well, we get some output. It was done in 0.04 seconds. Let me see whether I can plot this. Plot 7. There is a which parameter here that accepts a variety of values. You can read more about it in the documentation. But 7 gives us this linear plot. That's how it looks. So if we assume that there is no seasonality, then we end up with a model that doesn't fit the data very well. And we end up with this weird stuff, you know, straight line, and when promotion happens, it goes up. Obviously, it's not a good model, not a good forecast. But just to see how it works, okay, we got an idea. We can also compare this with the multiplicative error model. Wouldn't be too different, but you can see, for example, information criteria, and AICC tells us that the multiplicative error model is better than the additive error one. Okay, cool. What next? Now let's use all explanatory variables. We will use price as well, and I put dot here just to reflect that, you know, we include everything in the data, and I ask function not to be silent, so it produced the plot as well. And when we include price, things become slightly better, but we still missed seasonality, so it's still not an ideal model, right? What do we have here? Let's remember ACC 2136. Why am I not using seasonality here? I think the idea here is just to show how you can produce forecasts from such a model. And you know, you need to provide something like new data and tell it what the new promotion will be for the first one, for the second, and what the price will be for the period we are producing forecasts. But if we use holdout true, wait, we used it here, right? Yes, holdout true, then it will use the already available data, but if you use holdout false, you would need to provide it. Otherwise, it will produce something not really meaningful. Something like that. It will just assume, here is the warning, the new data is not provided. We will use last H in sample observations instead to do that. And it's not very good. Cool. Long story short, you can see there's lots of different things we can tune. So far, this was a better model than the previous one. Now let's finally introduce the seasonality. As I said, this is weekly data. So we need to tell the function that we have lags of 52, so 52 weeks in a year. Yes, this is not very accurate because, you know, in some cases you might have 53 weeks. This is simplification, but in our case, in our data, it was indeed 52. Right, so what do? We include all the variables. We now have MNM, so multiplicative seasonality, 52 logs. Let's see how much time it takes. Obviously longer. And it produces the forecasts like that. We can see that the fit is much better here, right? Because now we have the seasonal shape that we've taken into account. and the forecast is much more adequate because yes, we are not missing any important structure anymore. Let me have a look. Took 2 seconds to estimate 58 parameters, which is pretty good. Okay, doc. Yes, an AICC 2055. 2055. So it is indeed lower. Given how many more parameters we needed to estimate, you see the fit is indeed much better, and as the result, the information criterion went down. So this means that seasonality is really, really needed here. Okay, we can try adding trend, we can try model selection here. It would work. I don't want to spend too much time on these things here. Now when we want to produce forecasts, let's say for the holdout period, not the holdout, to include all the data and produce the final forecasts, as I said, we need to have promotional plan. So let's say for the next 13 weeks, we will have promotion 1 happening on week 6, and then nothing, and promotion 2 on these weeks, and we will fix the price of 2.8 pounds for the product. That's it. So you see, we sort of regulate these things, and this becomes quite useful. One thing, when you want to use weather data, then you're in trouble because you need to understand what weather you will have in 13 weeks or something like that. But in our case, we have explanatory variables that which we regulate. So okay, we can have this promo new data and see what the first strategy will be. So if we use this setting with promotions and prices, we expect the following sales for the next 13 weeks. We can change strategy somehow. Let's say we decrease the price to 2.5 and redo again, and we will see slightly different figure. So the idea here is that this becomes a quite useful instrument which you can use for different scenarios to decide whether to continue a promotion or not to continue it, whether to change the price or fix it, and so on. Right, so that's the rough idea. I'm not discussing here this dynamic mechanism here. It's done via regressors adapt code, and you can also trigger the selection of explanatory variables via regressors select, which becomes especially useful if you have, let's say, 30 potential explanatory variables and you want to decide which one to use. In that case, we will also use information criteria, and we will use stepwise forward approach, which is relatively fast. You know, it gives you a solution, maybe not ideal, but a solution. Right, should we take another 5 minutes? Give people time to see the workshop and maybe ask questions, right?
Yeah, yeah.
So we will continue in 11:10. Right, there is a question in the chat, actually, a couple. Regarding the static ETSX, is that equivalent of modeling the residuals from the ETS with a linear regression? Sort of. The only thing is when you do that using like that, you feed ETS, you extracted residuals, and then you feed linear regression, then you have two independent things, and as the result, you might introduce bias in some of them. So ETS might have higher than needed smoothing parameters and might overfeed the data. As the result, it will not capture the structure correctly. But that's one of the ways of doing things, indeed. The second one, which metrics were used to determine the model's performance? So there is a bunch of metrics that is available in the function. Let me show you. When we actually produce holdout true thingy and we fit it, then the model will have forecast errors here below. Lots of different things. My short answer which to use is something based on RMSE, because the model produces point forecast which corresponds to conditional mean, and as the result we should use either RMSE if we just look at one time series, or we can look at RMSSE, which is scaled version of this, and compare this if you have several time series and want to aggregate. There is also relative RMSE, which takes this thing and divides it by the RMSE from the naive method for this holdout period. Yeah, hope this sort of explains this thing, but we didn't discuss it for now. It would be, you would need just to calculate them and to compare. Yeah. Both good questions. Thank you for the questions. I love questions. The more questions I have, the happier I am. Right, one more minute and we'll continue. Right. By the way, in every of these PDF files at the end you have additional materials with some links. There are some posts from my website and some from Nikos Kourenzis, who also did lots of things on exponential smoothing. Really worth checking. Kidok. Now, intermittent demand, IETS model. So far, you see, we've worked with regular demand. It's the demand that happens on every observation. It's nice. The only thing you need to bother is the uncertainty about the value itself, how many sales we will have. But what if the product is bought not on every observation? So here's an example. This is from M5 competition, if I remember correctly. And what we see here is that sometimes we don't have sales at all. Then we have 3 or 4 or 1 and nothing again. This type of data exists in many different domains. It's in retail, in healthcare, in energy. The shapes and so on would be slightly different. So for example, in retail, it's typical that you end up with people coming and buying just 1 unit or 2 units of product, and that's it in this specific day. In healthcare, you might see some periods of time when people don't come to the emergency department, for example, and then they come in high quantities. In energy, you might have, the energy consumption which is a fractional number, not necessarily the integer one. So intermittent demand is important, and here is a simple definition. It is the demand that happens at irregular frequency. So you just cannot predict when specifically it will happen. Note actually the difference between the intermittent demand and count demand, because count demand assumes that you sell integer valued quantities of sales. You can have 0, you can have 1, 2, or 3, or maybe more, you know, depending on the distribution and so on and so forth. But intermittent demand says that there are periods of time when nobody cares about your product and nobody buys it. And this is the important distinction, because actually count demand can also be intermittent, or you can have an interaction. You can have, if we dive into statistics, then we will have things like zero inflated Poisson or zero inflated negative binomial distribution, which actually tells us that there's lots of zeros in the data, nobody comes and buys, and then they come and buy 3 units, something like that. But long story short, count demand is a different beast. It's not the same as intermittent demand. And as I said, there's lots of different examples. I've already mentioned some of them. Actually, the majority of the existing forecasting methods for intermittent demand come from this spare parts domain or something like that. You know, when you have engines, jet engines, for example, and you sell them 3 engines 1 month, then 0, 0, 0, then 5 engines, then again zeros, and so on. That was the original motivation for many methods. By the way, I will present this in a webinar on 14th of May. This is based on the paper that John Boylan and I have written. It was recently published in 2023, actually, in International Journal for Production Economics. And I will explain this in more detail. I will dive in the formulas and so on. But here you see we just have a brief introduction to things. So this model has 2 sources of uncertainty, and actually fundamentally we are talking about intermittent demand as the thing that has 2 sources of uncertainty. First, how much we will sell, but we've seen that already in the conventional regular models, and we denote it as ZT, it's demand sizes. And then when we will sell, so this is demand occurrence variable, OT. And demand occurrence is the variable that equals to 1 if we sell and 0 otherwise. As simple as that. And you have interaction between them, it's multiplication. It was sort of first discussed in Croston, but he didn't explore it from model perspective. But the idea is that you multiply, and you know when OT is 0, then we do not see demand. Although maybe there is a potential demand somewhere inside. So we developed something called IEDS. I wonder whether Apple will ever sue us for using small I in the name. We'll find out. And it sort of marries the intermittent demand approaches with the conventional ETS. What we do there, the core elements of this thing, is that we use ETS to model demand sizes. Then we assume that demand actually evolves on its own. We might not see how it changes, how preferences of people change when we do not observe the demand, but we assume that they might change. Then this OT variable follows Bernoulli distribution. Bernoulli means that it's 0, 1, you know. And if the probability is high, then we will see more ones happening. So we will see more people wanting to buy, and if it is close to 0, then we will see fewer people that want to buy. And then we use logistic transform for this probability and model this probability using another ETS model. So we now have, instead of just 1 ETS, we have 2. One lies for the demand, is used for demand sizes, one is for the probability of occurrence. We assume that probability of occurrence and demand sizes are independent. And I have this question mark and exclamation marks here because this is a strong assumption, and you can find in the literature that people challenge this assumption, and there was even some evidence saying that this is not correct. But it simplifies lots of things, simplifies mathematics and makes things tractable. And from my personal experience, it doesn't really matter. Although it sounds counterintuitive, but typically on intermittent demand you have quite small samples, very hard to estimate. And when you have these two models which are independent but sort of capture similar behavior, then you're still fine. And yes, this can be a room for improvement. So if anyone interested, we can actually discuss and develop a model that would loosen this assumption and have dependent demand sizes and occurrence. Maybe it will be even better. And then what we do, we just combine the two parts, occurrence and sizes, to get forecasts. That's in the nutshell what IETS is about. These are the core elements. Now, thing to note when I discuss this with machine learning experts, they have a mindset which comes from classifications and so on, that we want to predict whether this will be 0 or 1. In this setting, we typically we are not interested in that. Because we're capturing the structure and then we just have a probability of occurrence, which might, increase or decrease or change over time. But we use this probability then to make some decisions. And the conventional way of doing that is just getting for example, conditional expectation. You take the probability, multiply it by the point forecast for demand sizes, and you get your expected sales, right? Or you can capture uncertainty correctly. So for example, you produce upper bound or prediction interval, and you take this probability into account there as well. Because if you know that your demand will happen in 50% of the cases, then you know that your data will contain or expect to contain 50% of zeros. Then this will impact your prediction bound, right? How high it will be or how low it will be. Okay, now with the taxonomy of models here, it should reflect both parts for the demand sizes and demand occurrence, and becomes trickier. I indicates that we're dealing with intermittent, as I said, and here is an example. MNN MMN. The first bit, MNN, is for the demand sizes. So we are saying that demand sizes only have level as a structure and have multiplicative error. No trend, no seasonality. The second bit says that we have actually multiplicative trend in the probability. This would correspond to the situation when demand is building up or becomes obsolescent. Then in this case, either probability will increase or decrease. O stands here for a specific mechanism called odds ratio. This is the mechanism that regulates how specifically the probability is updated. We've proposed several different mechanisms. Here is a nice depiction of how the data would correspond to these different mechanisms. First one, fixed probability. We are saying that, nothing changes. It's just exactly the same probability that someone will buy our product. Then there is odds ratio, which has this nice behavior which is suitable for obsolescence. You see, we start with roughly 0.5, then things start declining, and after 10,000 observations, the probability is almost 0. This is obviously artificially generated simulated data. There is inverse odds ratio, which is good for demand building up. And we can see that probability increases. Then there is direct probability, which is very similar to odds ratio, but it is much more erratic. And then there is a general model, which I won't discuss today, but it is good for different combinations of these probabilities. The point here, we have several mechanisms, and we can use my favorite tool, information criteria, to select the most appropriate one for the data. Right. We also showed, actually, if you are familiar with forecasting methods like Croston and TSB, that we showed that this IETS model underlies those methods, which was actually the original motivation. I was trying to solve that puzzle, and then I got carried away and invented the whole taxonomy. We also argue in the paper that pure multiplicative models are more appropriate for both demand sizes and demand occurrence, but we need to have positive distributions for that, because when you have such a low volume data, normal distribution does not make any sense anymore. And this was another paper of ours, published also relatively recently, where we showed how we can use log normal, gamma, and inverse Gaussian distributions in ETS. And this changes the model estimation slightly, but also solves the aforementioned problem with normality. Now, if we deal with count data, the simple solution is rounding up, and it works well. We showed it in the intermittent demand paper. If you want to plug in some other distributions, it would not be straightforward. So if you want to have ETS with Poisson distribution, it will be a headache, because you cannot easily get the error term. Most probably, if you really want Poisson or negative binomial, you should switch to multiple source of error model, not to the single source of error. Cool. Let's have a look at R, and I think that we will skip multiple seasonalities today. You have the workshop there in the folder, so you can have a look in your own time. But let's see how intermittent one works. I use this for this example time series from M5 competition, the series number 2340, which was picked at random on one hand, but on the other hand not at random at all, because I wanted to see something that has a changing variability probability. You see, in the beginning it is here, then it starts going up, and then it slows down. So it should be an interesting dynamics. Yeah, there is a nice question from Yulia on chat. Can IETS include explanatory variables? Yes, it can. I went crazy and I implemented that in R as well. You can include explanatory variables in both parts, in demand sizes to capture specific, promotions, and in demand occurrence. In demand occurrence, this comes to the idea that we are saying that because of the influence of some factors, we expect that probability will increase, right? There is a higher chance that people will buy. So that's the logic there. Don't forget that it's always about probability. But yes, it is a good question. This is available in the function. Right, what do we have here? We have data, and what patterns do we see in the data? Not much. I would say just changing level and occasional zeros. I have a feeling that these long strikes of zeros here are stockouts. And I had a look at M5 data, and I see that there's lots of gaps like that there. I think that they face stockouts, so meaning that maybe the demand for the product is there, maybe people want to buy, but there is nothing on the shelves. Nonetheless, let's see how the model works in this setting. We can actually have a look. I should have closed all those things. We can actually have a look at this occurrence part, 0, 1. How do you do that? I will just create an OT variable, which is, equal to 1 when demand happens and 0 otherwise, and we'll plot it. I said I will plot it. Here it is. And I added red lowest line here, so it just smoothes the tendency that we have here. And roughly we can see that indeed the probability in the beginning was higher, then it started declining, and we've seen stockouts in this period, so probably this is why it declined, went down, and then starts growing up slowly as well. Lowest on its own is nice, but it is good for approximating things. You cannot produce forecasts with it. It just at least gives us some information. Okay, so the first model we will try is this odds ratio that I mentioned. This is how we call for it. I will use 28 last observations saying hold out true to see how the model performs. Let's go. All done. How much time did it take? Time is important in our world, actually. Time is money. Half a second. Okay, that's not too bad. But it didn't have many parameters to estimate anyway, and the sample is quite big, so it's good. Okay, so the code like this will tell Adam to fit ETS M and N to the demand sizes, and then to fit exactly the same model M and N to the demand occurrence, and we will have odds ratio model. So we'll end up with the fit like this, which is very hard to read and understand because of 1900 observations. But the first bit here shows us demand sizes, and well, actually it's the data, final data, and we see the purple line shows the fit, and it goes down when stockouts happen, which might not be the ideal thing, and there is some tiny small blue line which even I cannot see at the end, which shows us the forecast. And here this is the occurrence part, and we can see that the model is quite reactive. If what might have happened is that we might have some structure in the occurrence, and this is not being captured correctly because we have just level model. So we could try other models. For example, we could do the multiplicative damp trend. In general, as I said, multiplicative trend is dangerous, but when you dampen it, it becomes much well behaved. So let's see similar mechanism, but a different model. What does it give us? Model fit and forecast, and you see it's still quite reactive, and it produces not very realistic final forecasts. Why did that happen? Let's have a look. This is because the level is 0.39 and initial trend is quite low. Well, it's below 1, so we expect this declining trajectory, and the smoothing parameter for trend was equal to 0 or pretty close to 0, so it's not updated in the data. That's why it goes down like that. We can also automate things. If we use this YYN, then it will tell function to do multiplicative error, and then either no trend or multiplicative trend. And I've also suggested it to use automatic occurrence. So it will go through those different shapes that we have seen, like this, and it will select the one that is most suitable for the data. And then. Takes a bit more time. Why? Because there is selection for demand sizes, there is independent selection for demand occurrence, and then there is selection of the mechanism. And how much time? 6 seconds. Ooh. You see, the more things we have to select, obviously the more time we need to spend on it. And we get something like this in the end. So demand sizes, the most appropriate model was MMN, so multiplicative trend here, because I guess we see some decline happening here. With demand occurrence, it is still the local level model, so no trend. And we can produce some forecasts, and I'll zoom in just to see what happens with the final forecast. This is the zoom in for the last few months. The purple line goes like this, quite reasonable, and here's the final forecast, the blue line, and then the prediction interval. Let me stop a little bit here and explain what happens in this forecast call, because it is different to the ones that we've seen before. First, I explicitly asked to produce simulated intervals, because whenever we have multiplicative components or mixed components in ETS, we should revert to simulations which give us the correct prediction intervals. I've asked several levels just to see what happens with 90%, 95 and 99%, and I've asked only to produce the upper bound. In this instance, what it means is that we will ignore the lower one. Okay, it's drawn here, but it's not sort of needed here, because we know that the lowest bound in this demand is 0, right? There's no point in cutting somewhere above 0. Plus, for decision making, when we have intermittent demand, the classical decision in retail, for example, is to decide how many units we need to order. How do we do that? We just look at the upper bound. So here it is then. And I've asked for 10,000 iterations. So what happens is model simulates data, assuming the structure that we've estimated for next 28 steps. It has lots of different paths happening, and then it does it 10,000 times, and it takes quantiles to produce intervals and expectation to produce the point forecast. Actually, when it comes to intermittent demand, point forecast becomes not very useful. In fact, if you compare point forecast from this model with point forecast from simpler ones like Croston or TSB, you will probably find that they are very, very similar in terms of accuracy. And there's not much you can do how to improve it here anyway, unless you find a way to understand when the demand happens specifically. And on the other hand, we don't typically make decisions based on the point forecasts when it is intermittent demand. We want to, as I said, to stock products, or we want to decide how many patients will come, right, in 95% of the cases, which tells us then how many nurses we should have or how many doctors we should have. The lower bound does not play an important role, and the expectation is not very important either in these settings. Okie dokie. Another thing that I didn't do but is spotted by the function is this small trigger cumulative equals to true. If we do that, then function will produce cumulative forecasts. Let's have a look. They are not very useful when we look at things, when we depict them, but they become handy when we have this setting that we need to decide how many products to order for the next 28 days, waiting for the next delivery. And this looks much smaller, but if you sum up all the actual values in the holdout and look at the quantile that we've produced, you will see that most probably it is sensible, something sensible. Right, I'm not going to spend too much time here anyway. We're running out of time. Okay, so that's a very brief introduction to this model. As you see, there's lots of things left outside. I tried just to give you a general impression. Should we give 5 minutes of time? Although I'm not sure that we'll be able to do much with the multiplicative, with the multiple seasonality. Okay, let's do the following. 5 minutes, questions and answers, and then I'll just explain you the multiple seasonality, and you can take your own time to go through the workshop that we've provided. So we'll be back in 20 minutes past, and please, if you have any questions, ask. Right, there is a message from Kandrika. I'll read it out loud. How does ETS-X deal with overfitting? Since we have more explanatory variables, then we could end up with overfitting. Another question would... okay, let's focus on this one first. So how do we deal with an overfitting? By default, we don't. Which is a restriction, isn't it? But we can introduce different loss functions. For example, we could use lasso or something like that to kick off those explanatory variables that are not helpful. This is the thing that comes to my mind, frankly speaking, but this has not been investigated thoroughly yet. Another question, Kandrika says, correct me if I am wrong. If we refer to the odds ratio, if we have a longer sample size, the probability of occurrence is almost zero, but if we have a shorter one, it's more volatile. Exactly. Let me check. I'll find you the image like that. So yes, these things, these plots show you sort of the asymptotic behavior of models. Yes, in the beginning it changes and so on. It's quite fine. You can, if you have a data that doesn't exhibit obsolescence, this model should work as well without any huge problems. But over time, if we expect the demand to become obsolescent or something like that, this is what we can use. So yeah, in short term, it is more volatile. Right, the next one from Marco. Based on your experience, what are the benchmark models for intermittent demand, and are there models that work better? If we are interested in point forecasts, Croston, TSB as forecasting methods. If you have count data, then there is negative binomial model, which was discussed in Snyder 2002, I think, and there is zero inflated Poisson. They could be used as benchmarks. There is a very nice, neat thing called iMappa. So MAPPA, as I mentioned before, is the approach proposed by Korenzis, Petropoulos, Trapera. It builds upon ETS, and then they modified it for intermittent demand, and it seems to work quite well. In M5 competition, which had lots of intermittent data, XGBoost won the competition. So I think if you want to have very good accuracy, then switching to machine learning is one of the ways forward. But then when it comes to the uncertainty and so on, these things become less apparent, and maybe there are some, yes, there was an uncertainty track in M5 competition, and I must confess I didn't investigate it thoroughly, so I'm not sure what is winning there, but this would be quite relevant because we have intermittent demand and they focused on prediction intervals for intermittent demand. So I'm sure there are some good approaches there for that. Okay, about IETS, is it scalable? Suppose that you have to predict 10,000 SKUs. How fast it will be, I guess that's the question. As any ETS model, it is sort of scalable. In general, ETS is slower than regression, because in regression you have analytical solutions for the parameters, for the estimates of parameters. In ETS you have this recursive relation where the next value of state depends on the previous one. So with IETS it's a similar idea. The reason why it was 6 seconds in our setting is because I decided not to bother, and I told it, you know, select automatically components for demand sizes, components for occurrence, and this updating mechanism. If we apply it to lots of time series, then maybe we can be smarter in deciding what we want to choose. And actually in this paper that I mentioned, I used M5 competition data. I think I used a subsample of that data and I applied IETS to that thing. I don't remember how much time it took. It was done in parallel. my computer is quite powerful, but it probably took for one model maybe 5 minutes or so. But it would be for 5 or 10,000 of time series. So it's not very hard task to do. It is scalable. It's just the question of what you do and how you approach the problem. Okay, question from Harsha. In the case of a stock out situation, if we encounter sensed demand, how can we address this using the model? Is there any method to identify the actual demand? Very good question. My rough answer, I don't know. Well, I haven't investigated it with this specific model. There is a research in two directions. One, what to do with stockouts, and my colleague Anna-Lena Sachs from Lancaster University has worked in that direction. One of the approaches she mentions is that if you have, for example, a daily profile of your sales, you sort of understand how people come and sell, and then you see stockouts on the day. So this would be intra-daily, right? And if you see stockouts on the daily level, you can use this profile to sort of recreate sales. And this seems to be an approach that works well, but it assumes that you record things on, let's say, hourly level. And this is not always happening. So this is one direction, what to do with stockouts. You can interpolate somehow and assume something, and you can use your judgment if you're pretty sure that demand must have been this, if not for the stockout. But all of these approaches now use some assumptions, and inevitably you will end up with estimate of demand, not with the truth. Now the other direction is the sensed demand. I haven't done that with ETS or IETS. I'm not sure how easy it is to do. There is an alternative which is multiple source of error, sensed demand, and there was a nice paper by Diego Pedregal and Juan Ramon Trapero, published in 22 or 23, I don't remember exactly, where they used multiple source of error and they plugged in the sensed demand there, and it seemed to work quite well. But even if you do that, the problem with sensed demand is you need to sort of assume, you need to capture a structure with some assumptions, right? You still have assumptions inevitably. Long story short, whatever you do with stockouts, you should be aware that you are assuming something to fix the problem. And in some cases, assumptions might be quite good, relevant, and simple, and the others things become more and more complicated, and you need to stop not to overcomplicate things. Good questions. Let's then go through the rest of the presentation. As I said, I will just show you basics of this multiplicative multiple frequencies ETS. It is implemented in Adam as well, but there are other good alternatives. And yeah, we will not have an exercise. Now, here is a beautiful setting. Yes, by the way, thanks a lot, Kandrika, for posting the link to the paper in the chat, the link to the paper that I mentioned. Okay, so the setting, we have hourly data, hour of day. So we have hour of day seasonality and day of week seasonality, for example, right? What do we do? One of the simplest things, it was proposed by James Taylor in 2010. It's have something like double or triple seasonal ETS. For example, we can have this ETS AAA, and now I have M1 is the first frequency and M2 is the second frequency. So for hour of day, this would be 24, and for hour of week, it would be 24 times 7, so 168, I think. And here how it would be formulated. These equations are very similar to the ones that we've seen before in the introduction to ETS. The only difference is now we have two seasonal components. They have their own seasonalities, and we need to update them. So we have two updating equations for seasonalities and independent smoothing parameters, gamma 1, gamma 2. The model becomes bigger, becomes much more difficult to estimate. but it allows capturing seasonality in this setting, both shapes. We can actually use the multiplicative EDS in this model, in this setting, and I say in the brackets that we should do that. Why do I say that? Because we see more often multiplicative seasonality in the real data rather than the additive one. There are several problems. Oh, wait a second, no, I'll come back to that. So more often multiplicative rather than additive, and if we have this beautiful pattern, you know, hour of day, and then it changes for the weekends, for example, we'll see an example in a moment, then we will see that the variability changes as well. So this can be captured by multiplicative seasonal models, multiplicative ETS. I don't provide formulas here, but you can find them in the book. Right, so there are several problems with this approach. The first is ETS is recursive, and when you have high frequency data, let's say 10,000 observations, which is not actually a lot for the high frequency data, this means that the model needs to go through all the 10,000 observations from the very beginning to the end. And this, in the estimation of the model itself, it happens many times. You try these parameters, you feed the model, you get the some sort of loss function to understand how good the fit is. Then you modify the parameters, you feed the model again, extract loss, compare, blah blah blah. But this thing of fitting takes quite a lot of time, so it might become slow. Plus, estimation is not trivial because we might end up with thousands of parameters. With this simple setting with hour of day, if we just assume two seasonalities, hour of day and hour of week, then we have 23 seasonal indices for the hour of day and 167 for the hour of week. We add smoothing parameters, we add a level and trend, we end up with I don't remember exactly how, 175 or something like that. And this is already not a trivial task, right? Because the model needs to go through all those things, all the combinations, and come up with a solution in some limited time, because we don't want it to converge for hours, to work for hours. Now, another thing, pain in the neck, and the neck here is a very polite word, I should have used a different one, is the daylight saving. I never cared about daylight saving before two things happened. First thing, I started working on the paper with Bachman, Rustami Tabar, and Jethro Browell on hourly data, and I've realized that, you know, in one day of year we have 25 hours, and in the other one we have 23 hours, and go deal with that. So it was painful from the modeling point of view, but then another pain for me was when my daughter was born, and then all of a sudden your patterns change as well 2 times per year, and I hate DST now. I don't know what to do with it, but here it is. But the thing is, it is used in many countries in Europe, and as the result, your model needs to take this into account. You need to somehow to deal with it. This is one problem. The other problem is leap year. I don't know who invented 29th of February, but they did it, and we have it in our calendars, and you know, once per 4 years you have one more day than expected. The last bit is you might actually have some potential AR elements in the data. It was shown by James Taylor in his paper that when you add AR1, for example, you don't even need to go beyond that. You don't need to have a complicated ARIMA structure, but adding AR1 helps a lot for the ETS with multiple seasonalities. Cool. How do we solve these problems? There is a solution from De Oliveira. This is BATS model, and then the modification of it called T-BATS. You might have heard of it. It becomes more and more popular, and it's very good when you have high frequency data. T-BATS stands for this awful thing: trigonometric Box-Cox transformation, ARMA errors, trend, and seasonal components. So it is an ETS. Apologies for that. It is ETS with trend and seasonal, but you have more things upon it. The seasonality here is actually based on Fourier transform, but it is updated over time. And we have all these parameters. So it becomes very flexible, lots of things you can do with it. It's quite a nice model. It is a generalization of ETS, but you don't have error here because you use Box-Cox transform, and it solves the problem with fractional seasonality via Fourier. I don't think that it is aware of the daylight saving, frankly speaking, but I haven't looked at it thoroughly, so maybe it takes care of it automatically, which I doubt, but possible, but I doubt, but possible. The problem that it introduces is different one. So because we use Fourier, we need to select the number of harmonics, number of sine and cosine curves. And this is not trivial because, well, there are some methods based on spectrum analysis trying to understand how many harmonics you need to have, but how do you know that you need to have 10 here and not 9, for example? What you could do theoretically is to fit T-bats with 9 harmonics, then the one with 10, with 11, and select the one that has the lowest information criteria. But this becomes huge and very slow process. And by the way, it also has similar issues as the conventional ATS, where you, because it is recursive, so you need to go through whole the sample over and over again. An alternative solution, it's not, I'm not saying that this is a better solution, right? But there is a solution to that in Adam. How do we address the first thing? Estimation is slow and not trivial. We can use a different initialization mechanism because initialization is the core of the problem. As I said, we had 167 indices for hour of week. Instead of trying to optimize them, trying to go through all of them and decide which one is the best, use a different scheme. Backcasting that is shown on the slide means that we feed the model from the very beginning till the end, then we revert it and feed it from the end to the very beginning, and we get these states that we obtain from that. So we get our seasonal indices from the fit. We might do it several times and we get our seasonal indices, and then we use them for the final fit of the model, and here we go. We don't estimate seasonal indices per se, we just go through the data a couple of times and we get something that is driven by the data. My experiments show that backcasting is less accurate than optimization, but it is extremely fast. So if you want to get results like this is your guy. Now, another thing is you can provide initial estimates of parameters if you know them, or if you do this in a rolling origin fashion, then you can use the ones that you've received from the previous iteration. Daylight saving, a solution in Adam shifts seasonal indices by 1 hour 2 times per year. So when you know when it happens, the Adam will shift it to 25 or shift it to 23. The only thing here is that you need to use a zoo object which will provide dates, or something that will provide dates to the function. Leap year, similar shift. Once again, it's a fix. It's not, might not be the ideal solution. But then again, the question for me here, do we need to look at the day of year seasonality? Or maybe we should rethink the problem altogether. And potential AR, we can have ETS and ARIMA in Adam. So we can add there, the element there. If you really want to do Fourier series, it can be done using ETSX. So we can refer back to this chapter on ETSX with dynamic parameters, and it would behave similar to T-bats. Now, this thing that I've just described was used in the paper together with Bachmann and Jethro. I used Adam ETSX. Actually, it was Adam I ETSX for hourly data. It had the lowest RMSE from between all the approaches, and it had the smallest quantile bias. I'm not going to go into details. If you're curious, have a look either at the paper itself or I explained that on my website. But inevitably, if you want to improve the model, you need to spend more time on training it. The better you train it, the better results you get. And as I said, if you do rolling origin, you use smart initialization to get better results. I'll just show you a couple of figures, and then I encourage you to go through this workshop on your own time because we're running out of time. And this is a data of half-hourly electricity demand from James Taylor, his paper in 2010. And you I provide some examples here. So for example, we feed Adam M with seasonality 48 and 336. 48 is half hour per day and 336 is half hour per week. And I ask it to do backcasting in the initialization. As the result, it takes half a second to calculate, which, considering the sample size and the number of parameters to estimate, to fit, is very fast. So you see, you get this a simple model, which is not ideal, but okay in just half a second. We can analyze things in a similar way that we've done before. This plot shows you the split into components, and we can see that there is some structure left in the residuals, so we can improve upon it. Then there is a paper on the multi-steps losses, which takes more time, and if you use that, your error will go down. So RMSSE here is 0.538. The previous one was 0.867. So there are different ways how you can improve it, and I give you an examples with Fourier series and so on here to see how it works. And the final bit is TBATS. I've also done that for TBATS. On computer, it produced higher RMSE than Adam for this specific data. Doesn't mean that it doesn't work, but it was just like that in my setting. Although, to be fair, in that paper that I mentioned, here is the link to that paper in the workshop. In that paper, TBATS didn't work well for us either. I don't know why. Right. So let me close the session. Conclusions. In conclusions, what I wanted to show you in this workshop is how much flexibility you have with Adam. Yes, there is basic ETS, it works well in the default setting, but you can improve on it depending on different scenarios, which include regular demand, intermittent demand, demand with leading indicators, with explanatory variables, or multiple seasonal demand. There are more things, actually. There is a scale model there and other ways how you can produce forecasts. All of that is discussed in the monograph. Inevitably, you might need to invest more time to get better results, but there is no free lunch anyway, and it can be time consuming, but at least this is a flexible thing which gives you a nice tool to play around and to solve your problems. That's it from me. Thank you for your attention. If you have questions, please ask. Either unmute yourself and ask, or post them in the chat. Thanks.
Thank you very much, Ivan. It was a very eye-opening event, even for me. I guess let's give a few minutes.
Yeah, couple of
there are any questions.
Let me stop sharing my screen.
Especially the intermittent demand one, I'm looking forward to use it.
It's a fascinating topic in general.
Yeah.
But I will say, while people are thinking whether there are any questions or not, I will say something controversial. If you can avoid intermittent demand, avoid intermittent demand. Because it is a headache, yeah.
There are no questions on the chat. Thank you very much for accepting our invitation to be instructor for today. It was a very interesting session. Thank you very much again.
Thank you, Harsha. And thank you very much for inviting me. That was interesting for me as well. And great questions, by the way. Thank you, guys.
So, since there are no questions, we can wrap up the session today. So we are looking forward to our next session as well. So you all are welcome. Thank you very much. Thank you very much, Ivan, once again.
Thank you. Have a good day, everyone. Bye-bye.
Bye-bye.